So we need to consider roll, yaw, and side force for this lateral analysis. We're going to start with yaw, trim, and stability. So let's draw our simplified airplane here. There's our main wing, fuselage, and a horizontal tail. And Z is down, so a positive yawing moment. If we put our thumb into the page here, it wraps around to the right like that. And a positive beta is with the velocity coming in to the right side of the aircraft. Okay, so for trim, what we need is that the summation of moments about the z-axis equal 0. Well, if we don't have any lateral disturbances, then that is naturally satisfied. And if we do have lateral disturbances, then we find that yaw and roll are going to couple with side force. And so we're actually going to address this general trim problem later, where we satisfy roll, yaw, and side force all simultaneously to make sure they sum to 0. And instead, let's focus or talk for just a minute about stability. So for yaw stability, what we want the aircraft to do is if we're flying along at, let's say, 0 beta, okay, so V infinity is coming in directly into the nose of the aircraft here, and then we get some disturbance where the aircraft, say, rotates to the left. So our aircraft is rotated to the left. This is our fuselage line here. In fact, let me just draw it with a different color. So let's say that we're rotated to the left here. Well, that will produce some positive beta, which is actually the drawing that I have here with positive beta already shown here. So now our aircraft is rotated to the left relative to the free stream velocity. Okay, so we have some positive beta. Well, what do we want the aircraft to do? We want it to create a positive yawing moment so that nose will return back and be in the direction of V infinity, or the beta that we wanted to be at in the first place. So that requirement we write as the change in yawing moment with respect to beta. We actually want to be greater than 0. So with a positive change in beta, we want the aircraft to create a positive change in yawing moment to negate that change in beta. And of course, we can write this in coefficient form, Cn with respect to beta, and we're going to call that Cn comma beta. The change in yawing moment coefficient with beta has to be greater than 0. Okay, so this is our yaw stability derivative and requirement in order for the aircraft to be stable in yaw. And a good number for this is that Cn beta should be between about 0.06 and 0.15. These are numbers suggested by Phillips in his book. I can't say that I've seen them elsewhere, but I tend to trust what he has in his book. And so I would guess that that's a pretty good estimate of what you want your yaw stability derivative to be. Similar to like a static margin from our pitch stability analysis, we wanted that to be about 5%. That, of course, is just a rule of thumb, and this is also just a rule of thumb. You really want to do more analysis, including more of the dynamics of the aircraft, to really settle on a good number. But in the initial stages of design, this is a decent place to start. Okay, so this ability for the aircraft to change and minimize beta or get rid of beta, it will, if Cn beta is positive, then our nose of the aircraft will naturally turn into the free stream and get rid of beta. So if we have positive beta, then it will rotate to the right. If we have some negative beta, it will rotate to the left. This is sometimes called weather vaning. So sometimes you'll see that in the literature, weather vaning or weather cocking, weathercock stability. So this is kind of like the things that sit on top of the barns, right? That like the rooster, the metal rooster, whatever, that's always pointing into the wind. You know, it's got the little arrow on it. That's basically what it does. And speaking of which, an arrow from like a bow and arrow does a similar thing. It's got the fins on the back, and that produces both pitch and yaw stability as the arrow flies to keep the nose pointed into the wind. So that's the idea here. So for our aircraft to be stable in yaw, we want Cn beta to be greater than 0. And most of this is driven by the vertical stabilizer back here. So we're going to spend some time talking about the influence of that vertical stabilizer. That's the strongest effect we have on both trim and stability for yaw by using a rudder. So we'll talk about a rudder deflection on this vertical stabilizer, and we'll talk about those effects in the next video.